So yeah, as Ben said, my name is Ruslan or Ruslan, whatever works for you. I'm working for Intel. Since I'm new here, so it's like a couple of words about myself. So I'm also one API data parallel C++, one DPL lead developer. This is the library of parallel algorithms, and this is the talk about parallel algorithms. So I also have significant contributions to other products at Intel. For example, creating building blocks or one PDB, how it's called now. I'm a contributor to SQL, which is heterogeneous language for uploading, also open standard, and it was born, if I'm not mistaken, from OpenCL. I have some contributions to C++ standard. Before meeting in Bulgaria, I had 8 accepted proposals. Now I have 15. This is the T-shirt from Bulgaria that I just got. And also, recently I became SG1 concurrency and parallelism co-chair in C++ meeting. That's not it. I like singing, and I'm a pretty good singer. I'm a pretty bad guitar player. And it's like the picture of the guitar without me is not because I'm a bad guitar player. It's only because I don't have a good picture with the guitar and my finger. Recently, I became a father. My son is like 14 months old or something, and I'm also a mountain biker. That's why I'm living in Colorado. But this is the talk not about me, unfortunately. Let's talk about parallel range algorithm. So basically, the talk is based on the proposal that was and is, published as the C++ official proposal. We'll talk about this, like the fate of this proposal a bit later when I'm going to update the status. Although if you read the announcement to this meetup carefully, there is a spoiler already there. So let's talk about what parallel algorithms are in C++. Basically, those are algorithms that I think all you know, like for each sort, transform, many others, with the execution policy as the first template parameter and the first function parameter. It's instead namespace and taking iterators. I hope the code is visible for everybody, even for somebody who sits like at the end of the room. But that's kind of the font that going to be through the presentation. So if it's not comfortable for you, I suggest you to come closer. There are still some spaces. Sorry. Yeah, so basically this shows the serial algorithms based on find if, with some begin end, like 2 iterators and some predicate. And the parallel algorithms. The same API, but we have still execution bar as the execution policy as the first parameter. And by the way, I haven't mentioned, as I said, like I want it to be a conversation. I'll ask you questions, guys, during my talk. And also, if you have any questions, if you're not following, raise the hand. I'm happy to take questions as we go. What about parallel range algorithms? It's a proposal, yes. We also add the execution policy. Basically, it is the same, but we decided to constrain it with execution policy expedition only concept, because every algorithm is constrained in ranges namespace, and parallel algorithms are also not an exception. They are also in ranges namespace. They take ranges, iterator and sentinels, and execution policy as the first parameter. So as you can see, against the ranges find it, we have input, we have predicate, and we have also a parallel version of it with this proposal, which takes this execution par, input, and some predicate. And that's basically it. That's the end of my talk. Thank you for coming. To tell more, it's that simple as that. Of course, I'm joking. If it would be that simple, we wouldn't have been gathered today. Yes, it's much more complicated because it's an evolution. We kind of try to, let's say, take the drawbacks of the previous API, or probably not drawbacks, but still improve it. But before going to key difference, let's talk about our motivation. What we want to achieve is combining powerful ranges API with parallelism, which gives us opportunities to fuse several parallel algorithm invocations into one. With ranges API, we have better expressiveness, and for parallel thought in particular, and also ease of use. Let's look at the example. We have 3 calls here with the current algorithm style from phase, which is transform, reverse, and finding. Honestly, this is kind of artificial code, and there is a very specific reason why we use these 3 algorithms, and I'll talk a little bit later about that. So yeah, I mean, I can tell you the reason why it's artificial. The thing is, you can all wrap your iterator in reverse iterator, which is part of the standard, and also put this condition like I+1 to the predicate to find it, and just have one call. But still, for the demonstration purposes, it's a perfect example, in my opinion. So yeah, 3 calls. What we have? We have 3 algorithm invocations, and each invocation adds an overhead, because in parallel world we cannot go to the next algorithm, assuming like our execution policy that is passed here allows some threading. We need to wait, and before starting std reverse, we need to wait until transform is completed, and then before starting find if, we need to wait until reverse is completed. Yeah, so there is an example with fancy iterators, which combines all of those like in some pipeline, but not in ranges pipeline sense, still very similar. And as you can see, we have std make reverse iterator and dpl make transform iterator. We don't have any transform iterator in the standard. That's why we have to use third party, but still this code is possible, it works, and it doesn't complain at all. It solves the problem. It's one algorithm invocation, less overhead for parallelism, and the necessary work might be skipped. That basically means that yes, find if needs to find the leftmost match, but still, if we find some match, we can potentially, if the algorithm implementation support that, we can potentially cancel all the work that is to the right from the found element, and only continue to try to find something that is at the left, on the left side from this element. And this is basically the reason why the example was like that: transform, reverse, and I mean, it's because we have these fancy iterators, standard and third party, and also because in the future, I mean, on the future slides, you will see we have these views. So we just can go from C++ 17 example to the modern one. But that's not it about this slide. It's a lot of verbosity. I think everybody agrees with that. Also, I hope people online also can see my cursor. So basically, you can see that we pass and as the begin to transform iterator. It's logical because it goes in reverse, but it's still, you need to wrap your mind around that. And it's not super intuitive. Furthermore, this code doesn't compile. Can somebody tell me why? No ideas?
Different iterator types?
Again, please. That was right answer.
That's because the iterators are different. Because the iterators are different.
The iterators are different. So it means basically that the iterator types are different. And they are different because of two different lambda types. Yes, those look identical, but the lambda type itself, like even if syntactically identical, the lambda type is different for each lambda expression. So yeah, here is the explanation. We have find it, the old one, with first this first and last iterators. But the point is, as you can see from the template, the type is has to be the same. Otherwise, it's not deducible. GPL transform iterator, as you can imagine, just wraps an iterator and some functor. Then we have make transform iterator, which does two different types. So begin and end are variables of different types here, because func is the part of the template. And then, yes, we have compile time error for this. Actually, I mean, of course, it's not lambda 1 and lambda 2. Those are just some implementation defined types, but still, I think it explains an error. Yes.
Could that be made to work with type?
Of course, I mean we have a very quick fix. So very quick fix is
Obviously, this
this.
performance plus.
You just extract lambda from here, store it on stack before, and now we have one type.
Oh, I was thinking like, could you make an iterator with two different lambdas that have the same signature, for like, and then type erase them on storage, such that it works.
You can type erase them if your transform iterator is type erased. I mean,
Yeah.
if you type erase
There's
is,
performance cost to that, but
I mean,
potentially.
I think, of course, and I think nobody in the world, including std ranges use transform, implement that as type erase thing.
Sure. Yeah, I was just curious.
Yeah, I mean, sure, you can always wrap the function within it and be done.
But with ranges now we have iterator and sentinel, right? Rather than this is the classical interface of two iterators, but
Yep.
instead of
Iterator and
iterator
sentinel.
so they can be different.
They are, can be that, yes, this is absolutely true. We are all only considering the, let's say, the world without our proposal. So, is it clear? Fix is clear, I hope. The problem is clear. The example that looks ugly is clear. Okay, this is the example of the pipeline with all parallel algorithms. So now, after some paper, which the number like I forgot, but we can use pipeline, take begin and end from this pipeline of ranges and use it with all algorithms. It works as long as you have a common range, and common range is the range which basically has iterator and sentinel as the same type. To me, it also solves the problem. We have one algorithm invocation, and the unnecessary work might be skipped, but still a lot of verbosity, unnecessary verbosity, let's say. And it's only one algorithm. Imagine transform, which like binary transform, which has input 1, input 2, and output. You would need to write begin and then again begin and then again begin. The old transform has input like first one, last one, first two, and result. Okay, what happens with our proposal? From my perspective, this is the same code, does exactly the same thing, and now it looks nice. We have this policy, we have data, 5 with transform, 5 with reverse. Done. It still has a small problem. Does anybody know?
You said that it has to be a ranges colon, right?
Uh,
It's a view. Does this have a
views. Don't pay attention about namespaces. There might be mistakes, but this is not a mistake. Views are available from both std ranges and from std.
Yeah, I just meant I was wondering if that implied a sentinel iterator instead of that. Well, that's a different type.
Yeah, but here we don't have any iterator and sentinel, we have range. It's
Oh.
one argument.
Oh,
It's a pipeline, which gives you a range.
there's no parallel find if and ranges.
With our proposal, we have it,
Okay.
but without it, we don't. But with our proposal, that's exactly what happened. We have data, transform, revert, which combines in one pipeline, and we pass it as range. We don't ask for bigger than them. But still, there is a problem.
What's the return type?
Yeah.
Return type is an iterator, sort
What
of.
kind of iterator?
Borrowing
So
iterator.
it's not a single view or it's an iterator.
It's an iterator to found element. But I already gave a hint. It's a borrowed iterator. So what's the problem? If you try to dereference it, it doesn't compile because it returns dangling. You pass the pipeline as the temper. I wish, like, there is a guy in the committee which name is Zach Lane. I wish his paper lands at some point, which fixes that and makes transform view also borrowed. I'm not going to go into details why it's not borrowed today. It's like, I don't know, 10 to 15 minutes. I don't want to spend time on that. I'm happy to share it like in some private conversation after the talk. But the thing is, I mean, of course, you still cannot dereference it as is, right? Because it's fine. You need to check if it's and if it was found or not, basically. But if you try, even if it's like whatever you do with res, either compare it with and or whatever, it just doesn't compile because dangling and that dangling doesn't have any operations on it.
Can you explain what a borrowed range is? Exactly.
So borrowed range is basically a range which is like, oh, Ben, what do you want me to explain? What exactly?
So I understand the common range,
Okay.
so I'm not familiar with all the
Okay.
range terminology.
Okay.
So can you just tell me what a borrowed?
Okay, so in principle, borrowed range is the range that if you just construct it as R value, the iterator returned from it can be dereferenced. That's the simple explanation. So L value range is always borrowed range. And some views, let's say take view, is also borrowed range because there is one special variable that is specialized for take view, drop view, and some other views. The thing with transform is, I mean, okay, if you go into the details, fine. It stores lambda in view, and the iterator doesn't have like doesn't have this lambda stored within it. So it points to the view, and if view is destroyed, in that case, you have a dynamic reference to this functor. You cannot dereference.
So a borrowed range is like a view type that has some backing storage.
No, it's just a view which even if you pass it as an R value to find, it just doesn't dangle, like the iterator doesn't dangle if the view is destroyed. So the iterator of this view is self-contained.
I'm looking for, so what's the intuition for calling it borrowed? What's it borrowing from?
From the view, I think.
Okay.
The view it was produced from. Because like iterator belongs to view, you just ask like begin of something. In that case, like iterator, sorry, the find if returns you an iterator to the view which was constructed as data pipe transform pipe reverse.
Right, and that view is now gone away.
Gone away
So
after the algorithm
The iterator
invocation.
is dangling.
Yeah.
The view stores the lambda.
Transform view
stores the lambda.
Yes, and you need this lambda to make a dereference on the iterator.
And the result iterator just stores a pointer to that view.
Yep. It might be implemented differently, but that's the decision they made.
So a borrowed range is safe to look into. Is that what?
Yeah. So basically, yes. Like as I said, it returns borrowed iterator, which makes a condition. So if it's L value reference or it's specialized as true, for some view, then it returns an iterator, the actual iterator that you can dereference. But if it's not one of those, it returns a special type which doesn't have operations on it. And it just to avoid surprises at runtime, it just fails to compile.
Right, and so that's what res is here. The result
Is
a type which has no useful
stood
operations.
ranges dangling or stood dangling, I
Right.
forgot, yes.
So you can't
Yep,
use it for anything.
exactly, yeah. So the fix is also, is everybody good? Okay. The fix is also simple. We just, because of this nature of transform view, I mean, yeah, like the previous transform iterator that I showed doesn't have this problem because it's transform iterator, it stores lambda. Without Zach's paper blended, we have this transform view as is, so we need to store it before calling the algorithm, and then call find it on al value. So we are now safe to operate. So still, this code is perfectly fine. It's correct. It works, and solves all the previously mentioned problem, and it's still concise in my opinion.
But you have to be careful to make sure that you don't like return results from a function or something.
If these two lines are in the function, then yes.
But it's safe, it won't compile.
Yeah. It's still
Right?
one.
It doesn't have those operations.
Yeah, it has like, I think, either default copy constructor or whatever to be able to return from the function.
Sure,
But,
sure.
but then on the actual operation, yeah. If you want find if and then discard the results, I don't know why you need that, but go ahead.
I think that the answer here should be clear, but I'm just still a little confused. So if I somehow destroy pipeline in this instance, res becomes a dangling, a
Special type,
a special type?
yes.
Okay.
That doesn't, like, again, like, it shows, the algorithm return like some alias which does stood conditional for you, basically, which checks like, all right, okay, fine. I'll just return the actual iterator. If not, I return special type which doesn't have operations. And this is the only way how you can emit compile time errors.
Okay,
But if you, I mean, if pipeline goes out of scope here and you still have res, then it's dangling.
that's what I
It's
said.
not
Okay,
runtime.
if that's true.
It's not runtime, it's compiled.
Yep.
Good to continue? Okay. So, yes, there is another small bonus. There is an ability to use projections. I hope you guys know what projections are, but in principle, it's just unary predicate that you can apply before doing the actual predicate. For example, if it's a pair, you can apply, take first from it and apply predicate, what's called pred here, only on the first from pair. One of the common examples how we use projections. So if you're good to continue, hierarchy difference to existing algorithms. The execution parameter is added to existing, of course, ranges algorithms. It's obvious. The new set of algorithms requires parallel, new set of algorithms require random access range or random access iterator. It was not like that before. So we have also parallel algorithms that require ranges to be sized. This is not the case today. Serial range algorithm, I don't know why, but no, sorry, I know why. You can still go to the end like one by one without having them sized, but for parallel algorithms, it's basically crucial to have them sized. And D is the biggest difference. Right now, we convinced C++ committee that we need to take range as the output. I'll show you examples later, but the key point, like, don't mix it with output range. Is not the same. It's output range is the concept, and range as an output is the design aspect that we chose, and also were able to convince C++ committee that this is the right thing to do. The existing ones take iterators or like weekly incrementables, whatever fits the algorithm purpose. So here I'm going to show this Yes,
Do you have any, can you give some examples of
It's
ranges
coming.
which aren't sized?
yes, of course.
Like, what
Uh,
ranges might not be sized in everyday?
string literal. It's random access. It's even contiguous.
A string literal is not sized.
You don't know the size until you go till the end, right?
I can't show stuff,
Yes,
but a string literal is a char array, is it not?
Yeah.
So when you pass it to a function, it decays,
yes,
unfortunately.
yes.
Okay.
Yeah, and you can always create, I mean, I don't know why you would do that, but you can always create sub-range and say it's not sized, even if it was like the original range was sized in advance. But the first example that comes in my mind is like the string literal that is passed as the constant char. So yeah, here I'm going to show key differences in the code. Yes, execution policy parameter is added with the concept, an exposition only one, which basically uses the existing trait, is execution policy V. But this is pretty obvious. Now we have random access iterator, as I said, and random access range, and even for output. So far we didn't touch weakly incrementable and the second overload. We'll get to that because it's another detail. As I said, we also have them sized. So for the first overload, we make sized Sentinel-4, and for the second overload, we introduced a special sized random access range. It's again exposition only, and as like you can guess from name, it's random access and it's sized. That's basically the only reason why it's there. It just helps simplifying the standard wording a lot. And this is the fourth difference. Basically, we have now Sentinel for output, which is also sized as the template parameter and as the function parameter. And also we have sized random access range as an output instead of weakly incrementable, which was like almost an iterator. Yeah, here you can see like top to bottom comparison, the existing serial signature and the proposed parallel signature. Execution policy, random access iterator, sized Sentinel-4, random access iterator again instead of what weakly incrementable, and another extra parameter which is sized Sentinel-4 but for output. Execution policy is the function parameter and output Sentinel. And
The sized Sentinel support the distance operation or something like that then?
yes. So, and here is serial versus parallel, but range overload. Again, execution policy, sized random access range as the input, sized random access range as output, and then some shenanigans to return iterators instead of range, like asking range is iterator, asking range is forward iterator, and then again execution two additional function parameters, as execution policy and range as an output. So questions here? We will go into details for each aspect, why we think it's important, but this is, high level overview before going into details. So yeah, more about design. C++17 required requires CPP 17 forward iterate. However, in practice, all the implementations I know about, except Microsoft, support only random access. Our 1DPL implementation also supports forward, but only for one algorithm for each, and maybe some, basically similar algorithms which can be mapped to for each. Again, only Microsoft supports forward iterators, and there is a asterisk there because it's only from the implementations I know, the implementations that I studied. Maybe some others, but I'm pretty sure the vast majority comes with random access iterators. So actually, I had a very interesting conversation with Daisy Holman. Somebody could know her. I asked, why is like forward iterator? And she said, I think it was even input. But at the last moment, somebody asked, why it's input? And everybody says, yeah, let's make it forward for forward iterator. It should be good enough. I don't know if it's a true story or not, but I looked at the Parallelism TS, which had, some numeric algorithms like reduce or scan. I think it was reduce. And for reduce, I found that it really was input iterator in concurrency, in Parallelism TS. So maybe this is a true story, but yeah, after practice shows like we need a random access iterator for maximum possible performance. That's exactly what we're going to support and to propose, because it's the best abstraction in the standard for now. It excludes some potentially useful views like filter view, because it's not random access. It might be relaxed in the future, but don't get me wrong. I would put all my energy to not let it happen to relax to bidirectional iterator. If it's going to be relaxed, it's going to be relaxed to something in between bidirectional and random access, which is not in the standard today. So we need a new notion to support more views. But for now, what we have in the standard, random access is the best fit. Of course, it doesn't exclude contiguous. And size is necessary to know in advance for parallelization purposes. We definitely believe that if you know the size, you can basically somehow chunk it more efficiently. You can, if it's like small, you can even start serial execution instead of parallel one. You can also if it's like algorithm with input and output together. I'm going a little bit forward, but never mind. And someone is less than other, you can stop earlier. So you can skip also unnecessary work with that. And it's more memory safe. Like all the, modern meme copy with _s also have bound for both input and output. Do not assume that the output size is sufficient. So yeah, let's talk about ranges now. First, when we brought this proposal to C++ standard, there was a big objection to that. But we talk a little about objection a little bit later. Here are our arguments. We believe it's easy to use. And easy to use, I mean, if it's an iterator, you don't need to spell that ranges begin or like container dot begin. You can just pass range as is. Better memory safety, that's something we already discussed. Potentially better performance. Again, it's when your output size is smaller than the input size, you can just run a parallel loop on the smaller one. Let's say for copy. We'll see an example in a minute. And also an ability to detect an error. So first of all, there is no memory overrun, as we said. It's not an undefined behavior anymore. But also, if users do not want to, pass output range, which is smaller than input unintentionally, there is an ability to detect this error, because all the algorithms and ranges return you both, let's say, like iterators positions where they stopped for everything. If it's like 2 inputs, 1 output, then you have like all 3 positions, like 1 input or 1 output, 2 positions. Some algorithms like for each return you iterator, which is exactly 1, but also functor, where you can procedural ones, where you can accumulate something, let's say, have some state. But the objection was it's more complicated to switch between serial and parallel algorithms. So it's not like for certain algorithms like copy, which has output, it's not like adding an execution policy anymore. It's like a little bit more code manipulations to switch. Fine, that's fair. Then inconsistency with serial algorithms, that's fair, but I'm going to address it in a moment. Unclear semantics. Let's go to it. So first of all, this is about harder switching between serial and parallel. While this is true, there is an example which shows that it is already harder to switch in the standard today from state transform to state range transform. This is the binary transform that we touched earlier today. As you can see, it has both begin and end or first and last for first input. Only first two, it doesn't have a last two. And it also has like result, assuming that first, like the second sequence, as at least as big as the first one. And the output also. However, ranges version already does a different thing. It already, like for binary transform, adds the second sentinel and second range, add the range. So assuming that if one of the ranges is smaller, it's just going to stop whatever and it reaches first. But they didn't go further, and still we have, you see, like O result as the iterator. We went further, and now we also have it as range in our proposal. But that's about it. So basically, the key point here is yes, it's harder to switch, but it's not the first time in the standard. It's an evolution. If we understand that something was wrong or not good enough in the past, we fix it. The second thing is output inconsistency. Of course, we know that C++ standard is consistent in every single way. There is no inconsistency in C++ standard, right? Right, of course. So we can see copy, which has exactly what I showed. So basically, iterator and sentinel for input, only iterator for output, range for input, iterator for output. It's big incrementable, but let's think about it as an iterator. It doesn't matter. Those kind of details do not matter for understanding. We have an initialized copy, which basically copy, right? But instead of assignment, it just applies constructor. But it has range as an output. And it also has sentinel for the overload with iterator and sentinel, the sentinel for output as well. So, yeah, those are very similar algorithms. I, in principle, know the reason why. I think I know the reason. Nobody knows it for sure, but we discussed it with Jonathan Müller, who is the chair of SG9 ranges study group in C++ committee. And I think the reason is because copy supports something like back inserter. And initialized copy doesn't. But still, it's a precedent, right? And it's fully consistent, of course, right? And unclear semantics. I mean, while it's might be true, but honestly, all the algorithms work the way that they don't allocate. Somebody told me that this code might appear that it like it allocates and makes V2 as the exact copy of V1. Our proposal basically is to do what all other algorithms are doing right now. We want to execute to smaller range. And uninitialized copy does that. That's exactly what we propose. And I say algorithm here, but it's not actually algorithm, it's algorithms, because there is also uninitialized move, which is similar to uninitialized copy. But there is also partial soft copy, which also takes range as an output. Just a moment. For partial soft copy, though, it's an interesting story because range there is the way to pass the information how it's partial. So whether output range is finished, that's like it's like there is no point to pass bigger range in partial sort copy than the input. It should be smaller because that's why it's partial. Go ahead.
Did you consider having like a strict mode for this where like both ranges must like at the end be on their last?
Yes, we did. We decided that this is unfortunate because it's a precondition and it's runtime error. Sorry, it's an undefined behavior. We decided that since copy returns you both stop points for input and for output, you can detect an error yourself and decide what to do with that. You can terminate, you can, fix the bug in your code, whatever. Does it answer? Yeah, okay. And also, like, there was a point that probably somebody thought that in the committee, I mean, somebody thought that precondition might be better, but there was a point that you can always build an API on top of this one with the preconditions, if you like, if your library wants that, right? But you cannot do the other way around. If that's a precondition, you can just like return some results to users and then tell, let them decide, was it an error or was it not? So yeah, I think the first still stands, but it does not it's not a big deal given the evolution goes forward and we cannot stop it. Two others, I believe we addressed, at least in C++ committee, they were satisfied and say, yeah, like since it's an iterator anyway, you require random access, you don't support these back inserters and other weird things. This is the right way to do. And also the existing precedents ensure them that this is the right way, right thing to do. I have links at the end, but we wrote a complementary proposal, let's say, to the main one that explores ranges and output in details. So if you are interested, you can read about that and our rationales and all of that stuff. Are we good? Any questions? All right, let's go to complicated stuff. Copy. Here I'm going to show a bunch of code, but the thing is, yeah, let's actually start talking with the code.
I have a question, actually.
Sure.
Is partition one of the algorithms that is parallelizable?
Yes.
So then partition is parallelizable, but partition copy isn't.
It is.
So you don't know the size of the output ranges
We do
for partition copy?
with our proposal.
Okay.
I mean, even if not, we can always put a precondition that it's at least as big as.
Be as big as the range.
Yes.
The range.
Yeah. I mean, it's another precondition we wanted to avoid, but this is the precondition that we have today, right? How else would you operate?
I mean, in the ranges code or in the non-ranges?
In both?
Well, I mean, output iterators are weird, so the non-ranges,
Sure, but
like
that-
if you're not
that-
doing
that-
output range, you're just writing to a file or something, so it doesn't matter.
yeah, but anyway, this is the reality we live in. Yeah, I think
Well, I
our
was just thinking like, how would you parallelize partition copy? In ranges? So if you're interested to hear that.
the same way as copy. I mean,
Yeah, okay.
on the idea level, So yeah, let's talk about implementation a little bit. I'm going to show a bunch of code. So here we have an implementation that I saw in real, library or whatever, like framework, and the guy without names claimed that his copy if just worked perfectly. And I mean, it's not the exact code, but semantically it is the same. Let's figure out what's happening here, right? We take range size, then we work for each with iota, and then for each we invoke a predicate, and then assign the result if the predicate is true. Who likes that implementation of copy if?
Just producing a sparse output.
Yeah, like
Yeah.
with weird gaps.
Yep. So that's what's happening. So we have input 1744652379. Then predicate, which is basically check if it's odd or not, the odd number or not. The output is filled with zeros, and the result is, as you can see, like zeros are it's like stay on the positions where they are. But it's a gather algorithm, right? So it should like the result should be 175379 and then 00000 at the end. Yes, it's fast. Sure, right? It's fast, but it doesn't work properly. Copy doesn't.
Implement that. It's fast and it doesn't work.
I mean, and I mean, it's easily parallelizable, right, Ben?
That sounds like a no-op to me.
Yeah.
Return 0.
So, yeah, of course, it's wrong implementation. Copy if it's pretty hard to parallelize, but let's go into that. And to be clear, like my code that I'm showing here is just for demonstration purposes only. It's not optimized anyhow. It's just, and it shows you all the stages to just better explain the algorithm itself. It can be optimized further, of course, and be more efficient. But the purpose of this presentation is to fit the code on the slide. It was hard even like with non-optimal implementation. But first, let's just go through the like algorithmic idea before going to actual code. So here is our input. By the way, does anybody know how to parallelize copy? We can calculate mask. So basically having ones and zeros as the like another array, but actually as ones and zeros, not as true and false. Then we do scan.
Yeah.
And after that, you can see that we basically have the mask of indices, sorry, the array of indices that are duplicating each other, but we have exactly one unique index per mask value, which is 1. Now we have the array to copy into. And yeah, we just go like through for each and copy, as I said, like check the mask, and then where we have 1, we read this index from scan of the mask array, and then just copy the result there. This is the basic idea how it's parallelizable. Clear? Okay.
Is everyone familiar with scan?
No.
It's a basically partial sum.
Yeah.
You basically do like how to parallelize scan is another big story. I mean, if you can just, I think
Bryce has several talks that cover that.
Bryce probably has several talks that cover that. I think we can prepare a talk how TBB, for example, does that. And honestly, I don't remember from the top of my head. I know the ideas, but I cannot explain all the details, like how to make it efficiently. But in principle, the default scan uses plus, and it goes, it makes like partial sum. So basically, the next element is the sum of two predecessors. That's what's happening here. As you like, let me remove all these arrows. Like 0, like +1, that gives you 1. 1 + 1 gives you 2. 2 + 0 gives you 2 again. 2 + 1 gives you 3, and so on. Now everybody is familiar with scan. Yeah, sure.
Is that like a common chip instruction, or does something actually have to do with the scan?
So it's an algorithm. Yeah, we have this algorithm. I'm not sure if we have like chip instruction or whatever.
Okay, that's what that's.
Yeah.
To do the scan, wouldn't you have to know what's happening in the other, like I can see how this would work in a single threaded situation where you know everything across it, but if you're running it across multiple threads,
Yeah, you can do this. You can do this, but with, let's say you like, okay, you go into the details how scan is parallelizable, but in principle, you do partial sums and imagine that each block we call, let's say, work groups, right? And then you do synchronization
I
between
see.
work groups.
Okay, gotcha. Yeah, so I see.
You need to like the reduction value, the rightmost value in the first subgroup to be able to calculate scan between
I see.
subgroups.
I see.
Sorry, groups, like work groups. Yeah,
That makes sense. Yeah.
Yeah, but again, it's like on the idea level.
Yeah.
Scan is a building block algorithm. There's so much.
Yeah, for a lot of stuff, for this stuff, basically copy, partition copy, unique copy, unique as well, I think, all of this stuff, like remove copy, all of this. So yeah, let's try to implement this. If no more questions, I hope it's clear enough, because like if somebody needs one more time that I explain scan, just let me know. Because if you're not there, it's going to be even harder further. Okay, I don't see any hands. So let's try to implement this. And by the way, pay attention that I'll show you the code like from already as if our proposal would be accepted. So the range is transformed, which takes execution policy, then range, and then math at the array that we just created, like the dynamic array. And then again, this code is not like fully generic. I like some std move, std forwards, but here I specifically use std move on predicate and projection because I want to show that below this point, despite we have two more stages, we don't need those like predicate and projection anymore. We calculated our mask. We have all the information from user callables that we need. So we use transform. That's how we calculate mask. We write into that because the first range is the input and the second range, which is the mask, is the output. And then we just, return bool. No, not int as the predicate. Yes, I cast it to safety. So then we have this scan result. We just do std exclusive scan. Unfortunately, we don't have ranges, numeric range algorithms so far, but we wrote a proposal to add both. We don't have even serial ones. Except
Really hard to specify the concepts for numeric ranges.
not really. I mean, it depends on the way how you wanted to specify. For the existing paper, for the previously existing paper, it was hard because I think the path that was chosen was hard. We have fold family, fold left, fold right, and they specify concept. Yes.
Why is the type of the vector for the mask size t?
Because we need to do scan. We need that.
Okay. So we're
Yeah.
okay.
Yep. That's why we also, as you can see here, we cast the size t. When we, like, this is the value that we write to output. And our mask is size t.
Well, but in the mask, isn't it 1 or 0?
Yep.
And then aren't you using a separate vector for the output from the scan?
I don't think you have to though.
No, strictly you could do it in place.
No, because then you have for each that you also need to check both mask and index. You need to have both mask and index. I mean, yeah, you possibly could do this cast in scan, I think, to pass some custom lambda. But again, remember what I told you to everybody.
I just wanted to make sure I was understanding.
Yeah. Like, but the purpose is still the same, to feed the code on the slide.
Yeah.
It's still the same. So yeah, then we do std exclusive scan, and you can see how we need to write mask.begin, mask.end, scan result.begin, which I hope with our future proposal just becomes mask, scan result. Still is of use. And then we do, I decided to do zip. Since we have zip right now, zip view, I zipped all input, mask, and scan result, and then I just do for each. And in this for each, I check if my mask is 1, then I just write in the result by the given index the input value. And the way zip works, like if sum of ranges is smaller than others, it just goes to the smallest one. Questions here? There is a bunch of space, and it's intentional because we haven't implemented the case where what if the size is not sufficient, the output size is not sufficient, which is kind of hard to implement. You were first.
That for each, like, what's the parallelization scheme for that? Because you don't know like how many results are going to come out of that. Is that still parallelizable? Do you just like
You basically access each array here individually. There is no intersection anywhere, including even writable. For read, there is no races. For write, there is also no races because it's guaranteed that you have only one index for which, like one unique index for which mask is equal to 1 that you need to write. Absolutely parallelizable, as long as it's random access.
Yeah.
Right.
Yeah.
You guys said that, or the mask is size T because it has to be the same type of scan result. Is
It doesn't have to be, I guess. I think I could experiment, or like anybody from this room can experiment, whether we can just use bool and then, but of course not vector bool, right? That we would still need to write some either bool or wrapper type or whatever, and then write a custom scan predicate here to just cast this bool to size T when you do math. And I think the reason for that, if I'm not mistaken, in the standard, when you cast integral to bool, there is a guarantee that whatever is true is not 0 and whatever is false is 0. But whatever is true is not 0. It doesn't mean that the actual underlying value is 1. But when you count back, it's guaranteed that it's going to be 1, if I'm not mistaken. I think if you count back from bool to integral side, if it was not 1 even, but it was true, it's guaranteed to be 1. So that's why they decided to not mess up with all of this stuff and just create 2 size T's. Like again, we're not trying to save memory here. Then, yeah, go ahead.
Sorry, I probably have a lot of gaps in my understanding, and I still don't fully understand scan. But are we saying here that in that for each, that every single thread that this is parallelized to is processing the entire array and only copying, checking that mask for each index and only copying the ones that are essentially assigned to it?
You basically, yeah, you have chunks. Well, and how it's parallelizable, it depends fully of your framework. For example, TDD, like dynamic parallelization, it just determines like chunks automatically. If it's like OpenMP, I think they're going to be evenly divided on the number of threads, but still each thread will have individual piece of work, and you don't have any races between read and writes, because every index is accessible by one thread at the moment.
So then I'm still not understanding why we have to check if mask equals 1.
Because you don't need to copy, it's copy if, you don't need to check anything for which predicate is false.
Okay, thank you.
This mask is basically the result of predicate, it's not copy. Copy is simple, copy is just for each.
Okay.
Copy is boring. Copy is fun stuff. Go ahead.
This might be a silly question, but you're still having to do you're still having to like solve the whole transform and then the exclusive scan and then the for each.
Yep. It's 3 stages of parallel algorithms. And again, as I said, it's not the fully optimized implementation, but it shows you by stages what's going on. So it's blocking transform, followed by blocking exclusive scan, followed by blocking for each. But all of them are individually parallelized. So, and if you have like enough data, even that code will give you speed up. Does it answer?
Yeah, but if you have more parallelism, then in one of these blocks, you're still gonna use the full parallelism for each serially.
Yeah. So basically, if I understood correctly, like transform uses like let's say it's the only parallel algorithm that is run right now on TDB, right? It uses the full thread pool. Then the work is done. It shut down, like sends thread to sleep or something. Then you run exclusive scan in parallel. It also like wakes up all the threads, do some parallelization, then stops them again, like does the same for each. We also need to implement the return type. So we need to say where our input stopped and where our output stopped. For input, it's pretty easy. If we assume that input is always sufficient, we return last, right? While we didn't implement like another path where like the output might be not sufficient. For output, however, looking on these, does anybody have an idea how to calculate output stop point?
The last value in the mask, in the scan.
So basically, say it again, like scan.
The last value in the scan is the last index you write. That's it.
But not necessarily,
It's the largest index you write. It's not.
because you might have the last mask as 1 or last mask as 0. So it's basically the last scan of the mask plus the last value of the scan plus mask, either plus 0 or plus 1. Yeah, that's exactly what's shown here. So it's number of copied elements. Yeah. We implemented this part, assuming that the output is always sufficient. Now let's go to fun part. This code works. Now we have output as 7. Our implementation is still perfectly fine. So because 7 is exactly the number, like 6 plus 1, right? It's 7. Is the number of elements that we copied. And this is exactly the output size we have. But what if like our output size is 4? Question to the room. There are 2 design choices. Where should we stop? Okay, maybe there are more, but there are 2 reasonable design choices. Go ahead.
Stop after the scan when you can calculate the output range size.
Sorry, my question was done. Where should we stop at input? What stop position and input should we return?
For copy it, you have to go to the end, right?
No, if we understand that the output is not sufficient already.
Oh. You can keep a counter of how many passes are true.
Yeah, it depends whether you.
And yeah, of course, to do that, we, like in my implementation that I'm showing, we do full mass calculation. We do full, whatever, like scan, but then we know indices and we know the output size because it says the size of random access range. We can, we still do the algorithm like almost in full, except the last stage. But we still need to return the user the stop point in output so they can decide whether it was a mistake or not. So what to return?
You should return the iterated to 8 in the input there.
Okay, any other opinions?
I mean, you could return the end as the input, but the user already knows that you.
Any other opinion? Like Ben thinks we need to return to the iterator to these 8, right?
Yeah, that would be.
Ben, if you did that, what would you argue that, like, say that the last 2 values were flipped? Would you return 1 past the end, or would you return the like final 2? So like the final value, instead of being 2, 2, 2, 2, 3, it was like 2, 2, 2, 3, 2. Right, so the final doesn't match. Would you then return? If you were sufficient,
I
if you were
think you're
sufficiently
getting
sized.
to the very good point. Well, but let's I have this example. I specifically dropped 3 at the end to show at the end of the implementation. But let's first figure out, like for this very example, for 4 elements, there is an opinion that we should return iterator to 8, but that's not what we did in our proposal. We decided that we should return a different position.
Probably 9.
Exactly. Because all these things are false.
Yes.
Does that clarify the question?
Yeah. So basically, the first element that doesn't fit is 9. It's not an 8. And this is the useful information for the user. Because if we imagine that this tail is not here, like the 4 is the last element, right? You can just pretend that starting from 9 is not here. The algorithm is successful. We traversed all the input. I have this example further, but let's first see how we implement this. First of all, there are 2 interesting things that you can notice about the mask. The first thing that you can see that the mask is sort of divided on groups. Let's say in the middle at the end, there is a large group of 4, 4, 4, 4, 4, and then 6, 6, 6, 6, 6, right? But what you can tell for sure that only the last element from those groups will be copied. Because this 1 is always the last one value of mask is always indicates the last element of this group, and then it flips, like switches to another value, to the next value, and then it's not necessarily switches. For 7 it does, but then for 2 it does not, and then you have 6, 6, 6 multiple times until the end. This is the first thing. And another thing, given that we just add 1 at some point, this mask is sorted. With these 2, like with this knowledge, ideas?
You can do a binary search.
Yes,
Or
I
you could do a, what's the algorithm? Not mismatch.
upper bound. I can do upper bound.
Sure,
Mismatch is serial, upper bound is logarithmic.
right. But it depends, I don't know which is faster. Depends on the size of the input.
Actually, I think the good implementation, we haven't investigated it yet, but I'm pretty sure that in the real world implementation, which is optimized, we would hope to get this position naturally when we do scan,
Right.
without this extra upper bound stuff and whatnot. But for the demonstration purposes, I do upper bound. Go
Why
ahead.
don't you find if so that you can use a parallel algorithm?
We don't need to, because upper bound is again logarithmic. It's not linear.
Sure. But like, I guess like,
You can do that. It's still search, right?
sure, yeah. I'm not, I guess I'm just surprised that like, given the like size of data that you're considering, that you wouldn't want to stay in the parallel realm instead of forcing yourself.
And I think like for millions, again, like the maximum amount of logarithmic operation is 64, right? On the modern hardware. So it's 64n, which basically means it's like in practice it's 0.001 complexity.
Yeah, but it's all unpredictable.
I mean, sure,
Yeah.
yes, this is true. For demonstration purposes.
Sure, yeah.
No point, give it cash.
Yeah.
Yeah, I mean, if you want to create like the most performant implementation, that's not the way how you should it. Like you should do it. Like you should have like all performance like measurements, more clever way of using algorithms together, not splitting them on 3 stages, especially when you work on GPU, because you might end up with copying data back and forth from host to the device and like whatnot. We are discussing the idea here. We are not talking about the most optimized implementation. So what I do here is I do upper bound in scan result for the output size range. Sorry, for the size of the output range. And then I pessimistically do -1, assuming that the size is not sufficient at the beginning. And again, then I check if it's enough space, and I could do this check even before and not do all of this stuff. But remember the purpose, right? Like with extra if, the code would not fit on the slide. And if it's enough space, or there is another condition that I'll explain in a minute, I'll do +1 again. So assuming that I pessimistically jumped back, but I didn't need to. I still needed to stay in this position. And if enough space I should make +1 back. And if also the last iterator is basically the last element in the scan mask, that's the case you were talking about. And for these, the mask is 0, which basically means the algorithm is successful. We need to return and we don't need to return this previous element. And then we need to calculate the distance for each. We do this, like we calculate the distance here itself between begin and last iterator that returns from this array. And we now, again, let me switch back and forth. We had R, and now we have pipe with use take. So we just take this amount that we calculated. And then we also need to return the number of elements that was copied. So for input, we know that it's begin plus distance. We know exactly the number of elements that were copied. And for output, it's again still scan value plus mask, but it's the position where we stopped. Looking back, I mean, not looking back, look here. So if we stop, as I said, like here on 9, it's for sorry, where we stopped? Oh, I'm making -1. Yeah, it's 4 plus 0. 4 plus 0. Questions here? I think people glad that we recorded this, right? And yes, this again +1 that I showed you is exactly for this example that we were touching between Ben. And sorry, I forgot your name. I knew that.
Jonathan.
Yes, between Ben and Jonathan. So basically, if you have, let's say, output size 6, and you have 1, 1, 5, 4, 9, 7 to copy, you still didn't reach your end, but all elements there, I mean, for all elements at your tail, let's call it tail, the predicate returns false. Thus, the algorithm was successful. Now there is no point to return the iterator to these two. We just return the iterator to end, basically giving the users the information that all input was handled. You passed enough output size to embrace everything from input. That's the corner case we handling here. Like enough space, and this is the check that does this. Anyway, this code still might contain some bugs. I'm not pretending that it's like fully compliant implementation. I think it still misses the fact that the output range can be empty, but again, it's just easy check to add at the beginning and don't do anything. And we still are in our purpose to fit the code on the slide with this check. No. Okay, let's talk about simpler stuff. I think the complicated part is over right now. We have for each, which basically falls to the category of different return types. And sorry, I completely forgot to mention that these category colors are not like random. You will see them on the bigger picture than which algorithm belongs to which. So I purposefully split them on categories. For each, that's interesting. So we ended like one of our design goals was to keep the same return type between serial range algorithm and parallel range algorithms. But for each, it's problematic because it's not already the case. Basically, as you can see, stood for each returns something different to parallel for each, to parallel state for each, which is also something different to state ranges for each. And for even for like state ranges for each end. So I can explain you every single line except the third one. I don't understand why, honestly. But the point is clear, like the old algorithms like didn't return you input iterator, but for each return you function because you can put accumulate some state there and it will just return you a copy. And given that all the parameters to the algorithm are passed by value, this is basically the how it's called, like convenience API that doesn't force you to wrap it with reference wrapper or something like that if you want to accumulate some state there. For parallel algorithm, for each it's also clear because for them for it it's like the functor is copyable. Thus, threads can do as many copies as they want, and users should never rely on the fact that they can accumulate any state on this for each algorithm. So basically, that's why we return void. For this one, I don't know why it's in iterator. I mean, I know why it's in iterator, but I don't know why it's in iterator comma function.
Right.
It should be like that. I feel because it's the same in iterator is useful. Users don't have an iterator. If you don't remember the API shape for each n has iterator comma n. N is the number of the iterations. So they might not have the iterator to where the algorithm stops because, for example, for forward iterator, they don't know it and they would need to calculate it. I mean, this iterator themselves. But why if algorithm already does that? So iterator makes a perfect sense. But why not function? No idea.
Well, because it's a code smell anyway to have a stateful function for each.
In for each, no. Why? You just did, I don't know, like calculate something, do some debugging, like whatever. I don't know.
For each is for side effects. For each, if you want stateful, you should use other algorithms.
And I think you cannot because everything, in every single algorithm, there is a requirement that is regular invocable.
I think people accumulate.
Accumulate doesn't count. I mean, because actually, okay, I'm personally don't care about accumulate at all because accumulate is like C++.
Why do you care about for each then? That's my point.
For each is super useful in parallel world. For each and reduce are 95% of use cases.
Right. Yeah, but serial for each, you shouldn't care about. If you don't.
Oh, I personally don't care about. Yeah, sure. So the thing is, like, accumulate is not parallelizable at all. We have reduce, which is parallelizable in numerics, and also we now have fold, which is for some reason an algorithm, not in numeric header, but I don't know why. But still, yeah, it's also like serial by nature, but not fold. Oh, sorry, not accumulate. So then for ranges. For parallel, for each n, it's iterator, it's clear. For ranges, again, they decided to do what I think is right for each n. So borrowed iterator and function, and then for each with iterator and sentinel, and for each, and they return iterator and function. That's pretty logical. Based on that table, we ended up with this form. If you look at three last lines, in this table, what we did, we just dropped function. It's also pretty logical if you think about that, because again, we don't want users to rely on the fact that they can accumulate any state in the function. In the function, that's it. But iterator is not really useful for our API because it's random access. Users always have the iterator to end, but just for them to not rewrite the code, to not rewrite return type existing code, just switch to execution policy and parallelize it easier. There are two more algorithms that are special and also have different return type. Those are reverse copy and rotate copy, but I believe we don't have time to touch them today. It was a very long story. So, but there is a paper, I'll show you the link at the end. So if somebody is interested, I encourage you to read it. Yes.
Can you just give me that? So reverse copy, if you're passing the output range and its size, what more information do you need reverse copy to return?
Okay. A little bit of spoilers. Reverse copy and rotate copy, serial ones, always return last.
Wait, rotate copy?
Rotate
Serial?
copy and reverse copy serial ranges, rotate copy and reverse copy, always return last.
No, so rotate copy sucks.
That's not how I would design it, but I understand why they did that.
Well, rotate has to return where the first element rotated to. So if rotate copy doesn't give you like that, it's bad.
Yeah, we wanted to return stop point, but
Yeah.
that basically gives you a surprise if you switch to serial version to parallel version with the same return type. And then
I can see how rotate copy is nuanced, but reverse,
reverse copy always returns you last all the time.
yeah, what's the problem with that? So if in parallel ranges reverse copy, you have to pass the output range. It's,
We never,
but you allow it to be a different size from the input range?
yes, we allow it to be
Okay,
less.
okay,
That's why
so
for the
you have to
users,
return-
it's interesting where the algorithm stop, but then it
Yeah.
creates surprises at runtime. I mean, there is another reason, but again, it's like 30 minutes to explain. I mean, no, not today.
Okay.
It might be like a lightning talk, let's say, if you have some shorter talk on some other day, like trying to embrace like talks, like bigger one and shorter one and one meetup. Sure, I can follow up on that. But let's talk about like one DPL, one API data parallel C++ library I'm working on at Intel. So that's basically the source of our inspiration to come up with the proposal of parallel range algorithms. Previously, it was implementation of C++ 17 algorithms made by Intel for CPU only, for the host. If we talk about heterogeneous terminology, the product was called Intel Parallel STL, and we donated it to LLVM. And then GNU libstd C++ adopted it. So GNU libstd C++ now uses and always used our implementation of parallel algorithms. They are still experimental there, unfortunately, and the only reason for that is because they don't have a good enough default threading engine that would not have dependencies on third party. We provided them the implementation that works on TBB, but they say yes, we support that. If users want TBB, it would work on our implementation, but users need to opt into these explicitly. By default, we don't want to have any third-party dependencies. We also provided the implementation on top of OpenMP, but nobody tuned it seriously. So I cannot even say for correctness, not speaking about performance. Still need, to find some time to improve all of this. Then the evolution required us to implement also heterogeneous part of parallel algorithms, which can be run on GPU when SQL came, and when all of business of Intel was turned to like GPU market as well. Currently, it's part of UXL Foundation. It's some open governance organization which supports both one API specification and source code. So yes, we do have specifications, so anybody can go and implement like one DPL according to this specification, and it should be portable. I'm not aware that anybody does this in practice today, and I'm not sure what's the future. So we have 40 algorithms from this proposal implemented as experimental. Then we wrote this proposal, and when the design was more or less settled, we started implementing them as product quality. We have now implemented 35 of them. More are coming. And those two sets are not necessarily like a perfect intersection. Okay, I hope you still remember the example from the beginning with data, transform and reverse pipeline and find it. Let's see what it takes to parallelize it on GPU with one DPL. So basically, we create SQL queue, and I'm not going to talk much about SQL today, but this is the default way to submit some work to SQL. Then we use some special SQL allocator to basically make the memory accessible on the device. And we create a container of this allocated memory. So it's a unified shared memory. It's accessible on both host and device. And then we create sub-range of it because today, like one DPL doesn't support vector as is. Like there are some problems with that. Not sure if we will support it in the future, but who knows? And then you need to change namespaces to DPL find it, DPL make device policy of the same queue you created allocator from and allocate data from. And then pass this pipeline and predicate. Yeah, and I think that's it, yes. A little bit of work, in my opinion, not that much, but in principle, that's how you can run parallel range algorithms on whatever heterogeneous device that supports SQL. It's not necessarily Intel GPU. At least today we have a stack, I think, that runs also on AMD GPU and on NVIDIA GPU. Not sure about our further plans though, but at least today it should work. And there is some performance chart that we did. Basically, it's a speed up, and it shows like 3 calls, as it was at the beginning with C++17 API. Then it shows 3 calls with parallel range algorithms, like those 2 bars, and then piped range. This is all serial. This is all parallel. And yeah. No, I'm sorry. No, it's wrong. So it's all speed up, but this is on PBB on host. This is like 3 algorithm call compared to serial. This is 3 parallel algorithm ranges call compared to serial, and this is pipe range call compared to serial, and the same on GPU. Those 3 are on GPU, and like 10 is like 10x more than compared to serial. all of these numbers. I'll give you like 10 more seconds to look at it, and then we'll go further.
Is it the same serial implementation that we're looking at for each category? Like,
What do you mean the same serial implementation? Serial implementation is like I can envision only one reasonable serial implementation for many algorithms, except probably sort or something.
yeah, no, I think I answered that question.
Okay. Yeah, go ahead.
Why did you call the last side heterogeneous? Is that because it's not all STD? Or what do you mean by heterogeneous?
Heterogeneous means that you have GPU as the device you offload to.
Okay.
So you're not running on the same on the host, like your operating system is run on some CPU, but you heterogeneously offload to some other computation unit.
Okay.
Go ahead.
So he's using the not necessarily optimized slide version of these implementations that we've seen in this presentation, or are these some other implementation?
This doesn't involve copy that I showed. it uses the one DPL product implementation for everything except reverse. For reverse, we use some experimental because reverse is not implemented as product quality. But this is basically the I just remind you, like again, like 3 calls basically means like reverse, transform, and then find if. And reverse is from experimental 1 DPL, transform is from production 1 DPL, and find if from production 1 DPL. Those should be reasonably well optimized. I mean, we can still tune them more, but it's not like it's in product. All right, so the scope for this proposal and stuff. Those are almost all the algorithms that we standardize. And of course, I don't want you to remember all of them. How you should read this slide is basically what was in C++ 17 parallel algorithms is standardized in ranges parallel algorithms, except numerics, of course, because we touched that we don't have, unfortunately, reduce, transform, reduce, scan, transform, scan today, even serial ones in the standard. And those are new algorithms that were not in C++ 17. The reason for that is because all of them appeared later in the standard, since C++ 20 or later. And yeah, those are obvious. Those map to one of the existing algorithms. So why not just parallelize them? We know how to do this, and we have all the version on the right in this table that are parallelized. So yeah, we just added them. And out of scope algorithms are some algorithms that don't have any execution policy today. One of the obvious example is lower bound, upper bound, binary search, right? They are logarithmic. There is no point to parallelize them. And other algorithms like for which either parallelization is inefficient, something like that, shuffle, or yet to be proven and probably has very low applicability. I think something from partition family as well, but I don't remember all of them for sure. But yes,
Partition point is logarithmic.
Maybe, but I think there are also non-logarithmic ones, but which are hard to parallelize. We have the full list somewhere in our private docs, but again, it's for simplicity. What wasn't with execution policy was not added, except like the algorithms that listed here, but those are again not an existing stud namespace. Those are only instant ranges namespace. Algorithms from numeric, that's I already mentioned. There is the plan was to write a separate proposal. There is a proposal. We already partially discussed it in concurrency and parallelism, but not in ranges, unfortunately. But we hope to land it in 29. And like other algorithms that range namespace that are not mentioned before. So basically it's generate random, which is used to vectorize the random number generators and distributions. Only for that. This is like purposeful algorithm. And fold. Fold is specified as serial by nature. It goes either from left to right or from right to left. We need the ranges reduced, that is parallelized. Those are the categories that I promised. Basically, blue category is the algorithms with output, like copy, like initialized copy, like transform, which is here, where the main design question was like how to implement them, what's the behavior if the output is less. And the answer, as I hope remember, we execute to smaller range. This is the algorithm with output, but also with gaps, like copy if that we discussed in details. In these other algorithms that fall into this category are remove copy if, unique copy, partition copy, and set family. For each, for the special return type, and two algorithms that I mentioned earlier that we don't have time to cover today, reverse copy and rotate copy. This is the status in 1DPL. You can see all the algorithms that are implemented. We don't have any open PRs right now, I believe, for others that are coming. That's why I'm not showing, I mean, publicly available PRs. That's why I'm not showing it there, but we have plans to add more. I would probably spoil you a little bit if I would remember, but this is not the case. And also, like from U algorithms that we added, min max and min max are implemented. And as you can imagine, the implementation is super simple. It's just referencing the min element, max element, and min max element. Okay, this is the proposal status. It was hard work. Yeah. It's really hard work, and it's a huge proposal. Probably after the end of my presentation, I'll switch to that and just scroll with my mouse wheel, which can, you know, unblock itself just for an impression. Further work, as I mentioned, multiple types, numeric range algorithms. We are doing that. Also, synchronous version of parallel algorithms with senders and receivers. In principle, I think if it's blocking call, like synchronous call, I think we want to specify schedulers there, which basically indicates the place or the execution context where the work is needed to be executed. This is more control. Even bigger part of it, but even more unclear, is asynchronous parallel algorithms, like the high-level parallel algorithms that allow to be chained and then executed as the graph. And stretch goal is range as an output for serial range algorithms. I personally believe that that's going to be a huge improvement for both memory safety and also programmability. But I'm not sure, given 3 previous bullets, that I personally will have time to do this. I need to focus on first 3. But who knows? Maybe somebody here is interested to write a C++ proposal, or I'm not sure if it's first or not. I can assist if you like. There are some special things why it happened. I mean, why this proposal landed to C++ 26. First of all, this is my co-author and also senior principal engineer in our organization. I'd like to thank him a lot for all his support, for all the technical discussions that we had, for helping with the paper. He contributed a lot, not as much as I did, but still, yeah. I mean, all the going to C++ committee meeting and presenting our proposals there, talking to people. I mean, have any of you ever been in on C++ committee meetings? Okay, the hardest part is to get to the schedule because everybody competes to C++ committee schedule. So you should know people and you should know how to talk to them. So thanks to Jonathan Miller that I mentioned today, but for some reason, okay, it's I wanted to fix his name because it's a German name, but for some reason I forgot. So he is as SG9 Ranges chair. I want to thank him for his objection. He was objected very hard to range as an output design aspect, but that forced us to go and do our homework, to investigate it deeper, to return back with compelling argument. After that, he said, okay, withdrawn. So good stuff. Let's do it. To Inbal Levy. This is the chair of Library Evolution. Unfortunately, there was a deadline in Austria, which was before Bulgaria. And my proposal should be seen for the first time in Poland, which was even before Austria. But unfortunately, it was dropped from schedule. As I told you, this is the most problematic part. So she organized a out of schedule telecon in between Poland and Austria, where we looked at this proposal, and I believe because of this telecon, it was possible that what we have today, that it's landed to C++26. To Jeff Garland and Jonathan Wakely, those are chairs of library working group, the last stage in the committee pipeline, and they review all the wording. I'm very thankful that they were collaborative in organizing telecons. I mean, they do have telecons normally, but they agreed to put it on telecon schedule, so we were able to review it even before Bulgaria and put it on final stage in polls, and also leave a lot of room in the schedule for other important papers like reflection, like senders receivers, something else. What was another Cindy? Yes. And to Zach Lane and Jonathan Mueller, who reviewed my abstract for CPP Now, where this talk was seen for the first time, and the feedback they shared that the abstract looks good as is. But still, they put some efforts to review that. Those are useful links if you want to take some pictures. Those are the proposals I was talking about, like the main proposal. Then the range as an output paper, then reconsider rotate copy and reverse copy. And then some links to one DPL source code, one DPL specification, and SQL specification. And by the way, while I'm here, let me do what I wanted to do. Let me click on this link. And just as I said, like, let it load, and let me do 100 scale and do this. And my wheel stopped. It's a ton amount of work. So yeah. Basically, that's the main part that I have for today. We can finish here, but if you're still alive, I can show you bonus. It's up to you guys. It's like 5 minutes left. It's not a big example, but what do you want to do?
Yeah, go for it.
Okay. So yeah, I was talking about like better expressiveness. This is the example that counts words in some text. And again, like I am pretty sure there might be some experienced people with like Unicode, all of this stuff in the room. So that code might not work for like every use case, but it doesn't matter. So it just defines the way how we defined how we identify the word and how we calculate it in parallel. And with C++17, we take this string, then we do transform reduce, because we don't have, at least I tried to come up with something better, but I wasn't able. So we need 2 binary predicates. So we pass our text with -1, so one symbol less, and then we pass it the same, but with 1 symbol on the right. So we create this overlapping. So the first sequence has the text with without last symbol, and the second sequence has the text without the first symbol. And then we just transform reduce is a very weird algorithm from the name perspective, because transform is the second lambda and reduce is the first lambda. So first you do reduction and you cast it to int to return it as the value. Sorry, you do transformation. Yes, you do transformation. You checked it if it's like alpha and not alpha, and if it both are true, then you just cast it to int, and then you do a reduction. And that's how you calculate words. Is this example clear, more or less? Okay. And that's how you do it with our proposal, again, in parallel, as you can see in with execution par. With the new version of API, like we do count if, which is more natural for that, right? We have only one predicate, which takes like tuple because we zipped it. Like the sequence is the same. The first zip has the text without one symbol, and then the second sequence has with the text without first symbol. We drop, and then we read both, check them, return even as Boolean, because for count if expect is Boolean, we don't need to cast it. This is the exact same code with the new API. In my opinion, it's much more. It gives like better expressiveness compared to the previous one and does the job. Thank you for coming today and thanks for your attention.
Hi, could you help give us an intuition for the scale of data at which parallel algorithms are?
64 to medians. But I mean, really, like we also didn't expect, but sometimes people come and say, okay, your algorithm is parallelized bad on 64 elements. So, like there are some use cases, and yeah, if you let's say on dynamic parallelism like TBB, because of the work stealing algorithm, first of all, like, and I'm not sure like if you guys are familiar with work stealing, but in principle, in 2 words, first thread owns everything, divides the whole problem on tasks, and then makes part of tasks available for stealing, but it all takes time. So usually these small data sizes are very well parallelizable or something like that. But still, it makes sense that in parallel work. I'm going to even ask this for GPU if I'm not mistaken, but I might be mistaken. But yeah, usually medians and talk predicates, like how maybe computed predicates we have, whether it's like compute bound algorithm or memory bound algorithms. There are different trade-offs.
Could you talk through some of the different execution policies and their implications? When you might use them?
Yes, I can. So basically, first of all, execution policy are permissions. And those are permissions that users gives to the algorithm implementation what can be done with their lambda, what is allowed to be done with their lambda. So in other words, seek, like sequential execution, is the valid implementation for all of them, because it's the safe one. And I mean, if you're lazy enough, you can say, yes, my library implements parallel algorithm, but run all of them in like sequentially. It's a valid implementation. It's useless, but hell. So the example, like par and seek, is the most relaxed one. So basically, you promise that you don't have any synchronization in your lambda, you don't have mutexes, whatever. So it can be parallelized, and it also like some iterations, adjacent iterations, can be done simultaneously, like CMD, like vectorization, right? But if you say, let's say par, so we cannot vectorize it anymore, because for par, let's say it's valid for parallelized, but it also allows it to have mutexes within lambda, like have some synchronization, which basically means that some simultaneous operations on that would just get to deadlock. And then you implement, like you as the implementer of parallel algorithms, do your best from your knowledge of the properties of lambda. And again, I remind that the execution policy is the property of lambda. How to parallelize it based on your framework that you're using as the implementation. Like we use TBB as the default one on host, SQL as the heterogeneous one for GPU for the device. NVIDIA uses CUDA, for example, Cocos probably don't have the standard API, but they still use like everything, SQL, CUDA, whatever, to be portable. There is also Raja. I'm not sure what they're doing. Microsoft STL uses their Windows thread pool. LLVM C++ tries to implement them on their Grand Central dispatch, and GCC has, like Linux has nothing. Yeah, unseek is just says that it's allowed to execute some operations simultaneously, but it is not allowed to parallelize it. So that's basically the API of execution policy. But that's actually a good question. It's a big point of confusion even within C++ standard committee, because when people start talking about execution policies, you need to interrupt them and say, okay, before going deeper into this conversation, let's first all agree what execution policy means. And like people keep forgetting that even in SG1 concurrency and parallelism proof. Go ahead.
Now, you might have touched, is there an interface to specify the number of threads and on what course those threads should
No, no, it's totally up to implementation. I hope that the new API with schedulers from P2300 would also have some, not only scheduler to specify, but also some tuning knobs. No promise though. But we will try, but let's see how it goes. So the idea of standard parallel algorithms is, at least today, is mostly about like, it's a sort of easy button that you can use to parallelize something and get speed up, but not the speed of light. Also, from Bryce that we already mentioned today, I've heard, this is the NVIDIA guy, that the biggest complaint about parallel algorithms in the standard is exactly the absence of tuning knobs. So, but in my view, if you don't specify the scheduler, or in other words, the execution context to execute on, you also cannot specialize tuning knobs because you don't know what you tune for. That's why I think it's pretty logical to tie them together, like scheduler and some tuning knobs, at least some basic tuning knobs, probably not the number of threads because the thread pool may be already created, right? But probably some grain size or like word group size, like the chunks, how you want to divide it. And that's going to be pretty useful.